Hello, this is question 3, part C and D, the extended response, and we are now interested in these large oranges, which produce an amount of juice that's normally distributed with a mean of 74 mils and a standard deviation of 9 mils. Sure, why not? So we're looking for the probability that a randomly selected large orange produces less than 85 mils, given that it produces more than 74 mils. Well, this is a conditional probability, so we can use the conditional probability formula, which says that we need to take the probability of the intersection of these two divided by the probability that x is greater than 74. Okay, I often get questions about how to work out this intersection, and it's all about actually understanding what the picture looks like. So if you have some normal distribution and we have a mean of 74 in this case, so there's our mean of 74, we're looking for the intersection between x being less than 85, so let's say 85 is there. We're looking for the intersection between x being less than 85 and x being greater than 74. The intersection is where they overlap. It's where they're both true. It's an AND function. It's an intersection says the overlap. So there's less than 85. There's greater than 74 here. Everything here is greater than 74. Everything here is less than 85. So the overlap is here. So the overlap is where x is between 74 and 85. So we can rewrite that here. We're looking for the probability that x is between 74 and 85, divided by the probability that x is greater than 74. Okay, our CAS calculator can do that for us because we want decimal places. So the way to do it is to take, go to menu, and we want, whoops, that one's being glitchy. Let's try reloading it. We want a normal cumulative distribution function. And because we have these CAS calculators now, we don't even need to normalize things anymore. We can just put the mean and standard deviation in, and it does it for us. So you go menu, pop down to probability distributions, and you want a normal cumulative distribution function. Now, as you saw before, that top one is between 74 and 85. So the lower bound is 74, upper bound is 85. We have a mean of 74 and a standard deviation of 9. There we are, that's half our job done. We want that divided by the probability that x is greater than 74. Same thing, probability distributions, just use your cumulative one. If you want x to be greater than 74, the lower bound is 74, the upper bound is infinity, and we have 74 for our mean and 9 for our standard deviation. Okay, there we are, 0.778376, which to 3 decimal places is 0.778. Okay, now for a little more reasoning. So this fruit grower also grows lemons, which are sold, and the lemons arrive, and the manager there has a method to sample the product to see how good it is. And he samples 4 lemons and then decides if any one of those is underweight, the load needs to be rejected. So take 4 random lemons, If a single one doesn't meet the weight requirements, stuff it, we won't accept the load. So 3% of Manny's lemons are underweight. Now, you wouldn't need that process if that was known, really. But anyway, we want to find the probability that a given load of lemons will be rejected. Okay, well, you could define a binomial distribution, but really what we're looking at is finding out the probability of a load being accepted, and then we can take the complement. So what's the probability that a load will be accepted? Well, the manager has to pick 4 lemons that are not underweight. 3% of the lemons are underweight, so there's a 97% chance that they won't be underweight. And that needs to happen 4 times in a row. And we're assuming these are independent events. So we take 0.97 to the power of 4. Let's work that out. 0.97 to the power of 4 gives us 0.885293. 885293. Right, that's the probability of a batch being accepted. So the probability of a batch not being accepted is the complement, is 1 minus that. So it's 1 minus 0.885293, and we want it to 4 decimal places. So it's 1 minus that quantity, which is 0.1147. So that answer there is 0.1147. So there's about a 10% chance that the manager will reject the load. So right, now the manager decides to pick n lemons, and we want to know the value of n such that the probability of at least 1 lemon being underweight is greater than a half. All right, how do we do this? Well, one way to think about it is in terms of success. So getting lemons that aren't underweight and then taking the complement is probably the easiest way to go. So the probability of getting a good lemon is 0.97, and we want to put this to the power of n, and we want to find the value of n that gives us 0.5. Okay, so we want to solve for n. You can do that with logarithms, or you can do that with the solve function. Let's use the solve function. We're solving for when 0.97 to the power of n equals 0.5. Let's see what that gives us. 22.7566. So we get n equals 22.7566. Well, that doesn't answer our question because we want to know the integer value of n such that it just tips over this 0.5 point. Well, this takes a bit of reasoning here. Is it going to be n equals 22 or n equals 23? Let's try both and then we can do the reasoning. So let's take 0.97 to the power of 22 and 0.97 to the power of 23. Okay, so 0.97 to the power of 22 is 0.5117. 0.5117, and 0.97 to the power of 23 is 0.4963. Okay, which value of n do we take? Well, keep in mind what we've worked out here. We've worked out the probability that a batch is successful, that a batch is accepted. So the complement, the probability that a batch is rejected in each case is equal to 1 minus the probability that it's accepted. So looking at these two options, we're looking for the one that when we take the complement, it exceeds 0.5. Not when it exceeds 0.5 now, we're looking for the complement to exceed 0.5. So if we take the complement of these both, take 1 minus, you can see that this is the option that exceeds that 0.5. So this implies that n has to equal 23. We have to take 23 lemons such that the probability of at least one lemon being underweight exceeds 0.5. Let's work that out. What is that complement? Well, it's 0.4963 taken from 1. There we are. That's the value that just exceeds 0.5 there.